Welcome to today's Explainer. I am absolutely thrilled to have you here, because today we're going to do something pretty incredible. We are taking that theoretical textbook math you probably learned in school, and we're translating it into the actual applied mechanics of modern artificial intelligence. Look, we live in an era where data is the absolute foundation of almost everything, right? So understanding what's actually happening beneath the surface of AI, it isn't just a nice-to-have advantage anymore, it's practically a necessity. So if you're ready to demystify the technology that is literally shaping our world, you are in exactly the right place. Let's dive in.
So I want to start by throwing this question right back at you. Are neural networks just math? I mean, it is so incredibly easy to look at an AI generating stunning artwork, answering super complex questions, or even driving cars, and just assume it operates on some kind of digital magic. We tend to treat these systems like mysterious black boxes. But to truly understand them, we have to shatter that illusion completely. We need to peek under the hood and ask, what is actually powering these incredible feats?
Well, spoiler alert, the answer is yes. At its core, a neural network is really just a composition of smaller mathematical functions applied to real-world data to map an input to an output. That's it, the whole shebang. It's a familiar framework of variables and functions, the exact same concepts you studied in your math classes, matrices, functions, variables. These are the absolute bedrock of a neural network. The only real difference is that here, they're being unleashed on massive amounts of real, tangible data. Okay, so to make sense of all this, here's our roadmap. First, we'll cover the core of neural networks. Second, algebra in artificial intelligence. Third, calculus and machine learning. Fourth, graph theory and networks. And finally, we'll wrap up with real-world AI applications.
All right, part one, the core of neural networks, moving beyond simple polynomials.
So, if we look at this from the perspective of function approximation, neural networks present a remarkably powerful concept. In traditional math, you learn to approximate a function using polynomials or a Fourier series, and hey, that works great for straightforward problems. But neural networks, they take this a massive step further. Instead of just mapping a simple curve, a neural network can learn and approximate almost any incredibly complex function. Because of this specific mathematical architecture, these models are suddenly capable of processing and understanding incredibly dense data. We're talking high-resolution images, complex audio waves, and chaotic financial time series.
Moving on to part two, algebra in artificial intelligence, finding the alter ego of your textbook math. Okay, there is a direct parallel here that literally blows people's minds. Matrix multiplication from linear algebra functions exactly like the weights in a neural network. Seriously, if you've ever sat in a classroom crunching matrices by hand and wondering, when am I ever going to use this in real life? Well, this is it. You found it. These matrices determine how strongly one piece of data influences another. So that theoretical concept you learned on a whiteboard, it's literally the decision-making fabric of a modern AI model.
Up next, part 3. Calculus and machine learning, the engine of model training.
Now here is the absolute crucial point. Calculus isn't just about finding the slope of a curve on a graph. Those derivatives you learn to calculate in school, they are exactly what function as the gradients used to physically train a machine learning model. Think about it. Without calculus, an AI would make a mistake and have absolutely no mathematical way to understand how to fix it. Calculus provides the direction and the magnitude for the network to actually improve itself.
Let's actually walk through this continuous learning loop, because it's fascinating. Step 1, the model makes a prediction. Step 2, it compares that prediction to reality and calculates the error. Now, step 3 is where the magic, or actually, scratch that, where the math happens. Using the calculus chain rule, the network performs a process called backpropagation. It essentially works backward through the whole system to figure out exactly which weights cause the error. And finally, step 4. It updates those weights. This entire loop is fundamentally just an optimization problem. The network uses purely mathematical rules to minimize a loss function, constantly adjusting itself to get as close to the right answer as mathematically possible.
All right, part 4, graph theory and networks, visualizing the AI architecture. This perfectly illustrates how all these different branches of mathematics just unite onto a single structural platform. If you look deep inside, a neural network can be perfectly visualized as a graph. Every single node represents a neuron, and every edge connecting them represents a weight. For anyone who studies graph theory or network analysis, this is a massive aha moment. This fundamental blueprint is exactly what leads directly to some of the most advanced topics in AI today, like graph neural networks. Algebra, calculus, and graph theory all converging right here.
And finally, Part 5. Real-world AI applications. Taking this from the theoretical classroom to global industry.
So, what does this all mean in practice? Well, the practical applications of these mathematical models are vast, and they are reshaping global industries as we speak. We're talking about highly complex stock market prediction models, advanced risk management algorithms in finance, systems that conduct deep customer behavior analysis, and yeah, those remarkably conversational chatbots that assist us every single day. All of these rely entirely on the exact math we just broke down. What this means is that if you're studying mathematics, you aren't just preparing for a life of academic research. By understanding how these models work, you are securing a highly valuable place in the modern business and technology industry.
Which brings us to a perfectly summarized thought from our source material. Math gives us the way to think, neural networks give us the tool to apply it. I absolutely love that. The relationship here isn't just about mixing a subject with a piece of tech, it is this profound marriage of theory and practice. Your foundational math knowledge is literally the key to unlocking and solving some of the biggest problems of the future. So, as you watch the incredibly rapid advancement of artificial intelligence today, I want to leave you with this question. Now that you know the underlying math isn't magic, but a framework you can actually master, what will you choose to build with it? Thank you so much for joining me for this explainer, and keep learning.